Happy Friday. Our lesson today is comparing numbers in scientific notation. So that's twofold. First of all, I want you to be able to tell which number is bigger and which number is smaller. And then we're going to use that knowledge to say, okay, well, if one is bigger than the other, how many times bigger? And if one is smaller than the other, then I want you to tell me how many times smaller than the other one. Okay, so, all right, here we go. If we're comparing numbers in scientific notation, the number with the larger exponent is the larger number. Remember, the exponents are telling us how big the number is. Okay, the 8.5 and the 2.4 aren't really helpful if these exponents are different. So if I converted this to standard notation, that would be 8,500. And if I converted the other number to standard notation, that would be 24,000, because I'm moving the decimal another time. So 3 zeros here. So when it's in standard notation, it's really easy to see that 24,000 is larger than 8,500. But we could also tell by looking at the exponents. If they're the same, then we just look at the two numbers. Okay. The next one, we have exponents that are different. So the larger exponent, -3, is larger than -4. Remember, because negatives that are small are actually bigger. So that's the answer. Okay, here's some facts that I looked up online. The mass of the ship, the Titanic, is 5.2 times 10 to the 7th. And the mass of the Great Pyramid of Giza is 6 times 10 to the 9th. Which one of those has a bigger mass? Well, we've got an exponent of 7 and an exponent of 9. So the Pyramid of Giza is the larger one. Okay. Earth's moon, which is 7.3 times 10 to the 22nd, or Titan, which is one of Saturn's moons, is 1.3 times 10 to the 23rd. Larger exponent for Titan, so Titan wins. It's bigger. Okay, the HIV virus. If you had one copy of the virus, it would be 1.1 times 10 to the -18 centimeters, or the kilograms, or the E. coli bacteria, which weighs 1.3 times 10 to the -16th. Okay, remember we're talking about negative exponents, so the one that looks smaller is actually the bigger one. So the E. coli bacterium has a greater mass. All right, what if they have the same exponent? Well, then at that point you would be looking at this, the number in front of your times 10, because then your units are the same. So the exponents are both 3 in this question, so then it's either 9.3 or 8.52. So 9.3 would win there. -2 exponents for both of these. So the larger number is 4.7, and that would win. Okay, that would be larger. All right, the next few questions are based on this chart right here. It lists the years and how many cars were sold during those years. In which year were the most cars sold? Okay, so most would be the biggest number, so I'd first look at exponents. All right, I have 2 that have exponents of 7. So if I want to know which one's bigger, I then have to look at the 1.8 and the 2.4. And the 2.4 is larger, so 1980 is when the most cars were sold. In which year were the least cars sold? In other words, the smallest number of cars. So I look for the smallest exponent. Okay, we're tied for 6s. And so the smallest value of 3.8 for 1990 would be the least cars. How many more? How many more cars? We're having a little throwback to lesson 1-7 where we're setting up a subtraction. Were sold in 2000. So 2000 was 8.9 times 10 to the 6th. How many more means subtract? Then 1990. So that's 3.8 times 10 to the 6th also. Okay, so this actually has same exponent, so you can use the shortcut if you want. You can use the calculator if you want. You end up with an answer of 5.1 times 10 to the 6th. Now, some of your homework problems are different formats. For example, you might have one of your values in scientific notation and one of your values in standard notation. So what you need is for both of them to be the same. And it doesn't matter to me whether you're picking to make both of them standard or both of them scientific. So let's say I decided I was going to make both of these standard. So I would take this decimal and move it over 1, 2, 3, 4, 5, 6, 7 times. I need 1, 2, 3, 4, 5, 6 place holding zeros. So when I write it out correctly, this is 34 million, this is only 4 million. But it's hard to tell just by looking at the two formats. So you're not really sure. You really have to have them in the same format. So now I can see that that one is larger. I could also have written this number in scientific notation. Put the decimal here, so 4 times 10 to the 6th power. I could see that this has a 6 exponent, that has a 7 exponent, so 7 wins. Alright, the next one. I see that we've got scientific notation and standard notation. So here again, you can convert 3 decimal moves, 0.0092. This other 0 kind of went off the white part here. It's hard to see. And if I do that, I see, oh, they're the same. If I made this one into scientific notation, and I want to stress you don't have to do both, just pick one. That would be to the -3 power. And, oh, they're the same. So whichever one you pick, you could, just as long as they're the same, you can compare. All right, this has the word million written out. And you have to know how many place values million is. Million has 6 place values after it. But when it says 4.5 million, I've put the 4 in the millions place, the 5 after it, and fill in the rest with place holding zeros. Okay, well that's still standard notation, and this is scientific notation. So I still have some converting to do. Either I can convert this to scientific, so 4.5 times 10 to the 6th power. Okay, and then I can see that, oh, they have the same exponent, so 7.2 is larger. Or I can convert this one to standard notation and get 7,200,000. So 4,500,000 or 7,200,000, I can see that the 7 million one is bigger. Okay. 9.3 times 10 to the 8th or 4.3 billion. Well, 4.3 billion is, you know, billions, just like millions, it has a certain number of place values. Billions is 9. Okay, so 4 goes in the billions place, 3 follows in, 4.3 times 10 to the 9th. Mrs. Andrews, why didn't you just write 4.3 times 10 to the 9th? If billion is always 10 to the 9th, why didn't you write that? Well, because if it's, you don't specifically have to write, if I had said 14.3 billion, we could not write 14.3 times 10 to the 9th. That would not be correct scientific notation. So I don't advocate just automatically putting 10 to the 9th for billions or 10 to the 6th for millions, because if this was 14 billion, we'd have to move the decimal over to make correct scientific notation. So I can see that this is going to be to the 9th power, this is to the 8th power, that's bigger. So now that we can tell what's bigger and what's smaller, the next thing we're doing is determining how many times bigger is it. So we end up setting up a division problem, and the division problem is always going to be the larger number over the smaller number. Okay, larger over smaller. So out of these two values in our first example problem, I see an exponent of 6 here and an exponent of 3 here. So I'm going to put the larger exponent on top and the smaller exponent on the bottom. Now remember, when you type these into the calculator, to put parentheses, otherwise your calculator does not give you the correct answer. And when I type this in, my calculator spits out 3,500. Now, the nature of these problems is we're probably going to be getting fairly small answers, okay? Maybe a few thousand or a few hundred. I'm going to say it's not really worth answering in scientific notation, okay? 8.75 times 10 to the negative 3 is how many times greater than 3.5 times 10 to the negative 5? So our rule is we put the larger value on top. So my exponents are negative 3 and negative 5. Remember that negative 3, even though it seems smaller, is actually the larger value over 3.5 times 10 to the negative 5th. So we punch that into our calculator. Don't forget, when you put it in your calculator, to put parentheses around your numerator and your denominator, and you get 250. Okay? Let's say we have an ant colony. One ant colony has 2.8 times 10 to the 4th ants in it. The other ant colony has 5.6 times 10 to the 6th ants in it. How many times larger is the larger colony? So the larger colony has the larger exponent, 5.6 times 10 to the 6th, and the smaller 2.8 times 10 to the 4th. Parentheses. Okay, and you get an answer of 200. 200. All right, lastly, some of your homework questions this weekend are going to ask you what fraction of something is something else. And this is the reverse of what we just did. If we're making the fraction, we want the small number on top and the big number on the bottom. So if I am doing the first example, the smaller number has the smaller exponent, so 2.4 times 10 to the 4th over 3.6 times 10 to the 6th. Again, we're going to divide that out with parentheses. And our calculator is going to say 0.006 repeating. When you get 0.006 repeating, and we want to make a fraction out of this, remember that you can Sorry, I'm typing at the same time. Your calculator will convert decimals into fractions for you. You hit the second button, and then diagonal from that is a button called PRB, and we don't care about the PRB part, but on top it says fractions and then double arrows and D for decimals. So that's the button that will turn any fraction into a decimal and any decimal into a fraction. So if I do that button, I get 1 out of 150. All right, let's skip right to the king-cone problem so we're not lasting forever on this video. King-cone estimates that they use 4.5 times 10 to the 9th sprinkles every year. 3.6 times 10 to the 8th are rainbow sprinkles. What fraction are rainbow sprinkles? Okay, so the smaller number this time, exponent of 8, goes on top. 3.6 times 10 to the 8th. And our larger value goes on the bottom. And don't forget to put this in parentheses before you type it in. Okay, so when I type that in, I get 0.8. And if I take that 0.08 and I hit second and the fraction to decimal button, I get a final fraction of 2 out of 25. All right, I hope you have a great weekend, and I will see you next time.